I'm Joe Hayes. I'm from the Naval Research Laboratory. I'm going to talk to you a little bit about edge intelligence. But I thought what I would do to start off is to help you understand a little bit about what the Naval Research Laboratory is. So about 100 years ago, the Secretary of the Navy reached out to Thomas Edison and said, hey, we need to establish a laboratory to be able to make advancements to ensure national security. We are primarily based in Washington, D.C., although we've got a number of sites, and I'm blanking where they are. I know there's one in California. There's one down south near the Bay or the Gulf, Stennis. Anyway, it is structured much like an academic university. There's a large variety of different divisions and focus area, as you can see there. We, unlike other research laboratories, the Navy established NRL as a capital working fund. That means we don't get money from Congress. I mentioned that during the funding session. The top little section here, 18%, that's the only amount of money that we actually get from Congress, but we don't get it directly from Congress. It comes through ONR, and then the money shows up at the lab, and then all the PIs compete for that money. The rest of the money that comes into the lab, we write proposals and compete to win those funds, much like a defense contractor. So that's why earlier I described us as a defense contractor within the government. Okay, so there's a long history at NRL. I'm not going to belabor all of this. We've got history in the nuclear submarines and space. A couple other, well, there was one about radar. One that you might all, well, most of you are most familiar with about GPS. Most people think about the Air Force. No offense to our Air Force buddies. The patents for GPS are actually held by NRL. NRL builds one-of-a-kind systems, and then we transition them. So NRL developed timation or GPS back in the 60s and the early 70s. Once we proved that it was possible, we transitioned that. And you know, the big network that everybody uses today is credit goes to the Air Force for that. But the technology was developed at NRL. My division specifically, or directorate, I think actually the next slide talks about this. We've developed well over 100 unique satellites. Each one of them is unique and different, solves a different purpose, and we've transitioned them off to sponsors or off to industry. And you know, this is the bread and butter of the division that I come from. So I'm in it. Ed, who you just listened to, comes from the Naval. What's it stand for? Ed, Naval AI Center of something. Naval AI Center. Let's just say that. And I come from the spacecraft engineering division, and so does Sam. So I'm going to talk a little bit now about some work that we do in spacecraft engineering before I get into the specifics of the edge intelligence. Many of you may, okay. So just to give you a little bit of a roadmap, within spacecraft engineering, there is a more focused, smaller group of which Sam and I are a part of that focuses on the robotics side of spacecraft engineering. And we have a roadmap that predominantly focuses on space, but we also, because we're the corporate research laboratory for the Navy and for the Marines, we also deal with maritime, I should go this way, Navy and Marines, right? So we have some land-based work that I'll talk about, as well as there's some littoral related work, which I'm not going to talk about today. All right, so has anybody heard about the DARPA RSGS program? Does anybody know what that is? Okay, so this is, I've been told, this might be apocryphal, it is the largest DARPA funded program in DARPA's entire history. It is developing effectively a space mechanic, a robotic space mechanic. So we launch a mechanic up into space, and it goes and services satellites that are in orbit. These pictures here are showing our space robotics lab in our building. It's an 18 degree of freedom system. You got two gantries that are 3 degrees of freedom, and then you got two big industrial FANUC robotic arms, 6 degree of freedom arms, and we're able to put mock-up back ends of a satellite on one side and a servicer on the other, and then the system is big enough to where we can actually simulate the kinematics of an orbit. And then during that simulation, we prove out tests related to mechanics work that we're trying to develop within the robotic system. So here's 4 examples systems. One is just the ability to inspect an asset that's in orbit. Another one is what I call a space tugboat. If you spend $1 billion on a satellite that has to be in a certain geo slot, and that satellite, for whatever reason during launch, gets into the wrong slot, or it doesn't even get in a geo slot at all, the satellite can be fully functional, but it is now space junk because it can't complete its mission. And all it needs to do is have somebody come along, grab it, pull it into the right geo slot, let it go, and it'll perform its job. That actually happens about 1% of the launches if you take U.S. history. Another one is if you get a stuck panel during deployment, you know how the solar arrays, we fold them up at launch time, and then when we get into orbit, they unfold out. A lot of times they'll get stuck. Well, I shouldn't say a lot of times. Again, a small percentage of the time they get stuck. All you need to do is go up and flick it, and it'll deploy out, and the satellite will be functional. But with it being stuck, it doesn't get the power, therefore the system dies, and it starts tumbling, and you just lost, again, multi-hundred-million-dollar asset. And then finally, upgrades. So you can go to an old system that was developed 20 years ago, and it's coming to its end of life. And simply by coming up and upgrading the electronics or refueling it, you can extend the life of that servicer, or sorry, that satellite. So these are some tests that we've done within the lab in preparation for the RSGS launch. So RSGS will be launching a demonstration, first time in the world, to show servicing on in orbit in about 15 months. It'll be summer of 2024. So why am I talking about this? This has nothing to do with Neuromorphics right now. All of this work is all of the control algorithms for this robotic system are classical control. The techniques were developed in the 60s. It's has nothing to do with Neuromorphics, right? Well, the reason why I chose to talk about it is it establishes a good motivation for why our group has engaged in developing expertise with Neuromorphics. In space, power is king. We have a very hard time managing the heat generated from systems that are consuming power. You don't have convection. You only have radiation. And so that thermal management is a very strong, very challenging problem. Second problem is because at times we have very limited amounts of power, the ConOps that this mission is going to follow, we have multiple arms to perform the servicing, but they only operate one arm at a time. And the primary reason is because space-rated processing is 20 years behind the times due to the rad hardening and all that. Therefore, they don't have enough computational power to be able to operate multiple arms at the same time. Stated another way, if our goal is to push more autonomy and more intelligence onto these systems, that's going to increase the amount of computation that needs to happen. And, it'll be a problem for these autonomous systems. So we have to change the paradigm how we're building these systems. All right, so with that, now I'd like to talk a little bit more about the edge intelligence. So again, to this community, this is kind of obvious, but edge intelligence really is us building in this capability of bringing intelligent policies and bringing it close to the sensors and actuators. By bringing that intelligence close to the sensors and actuators, we don't rely on a link to Earth. We don't rely on a link to some other system or some other location that has the compute. All of the compute can happen directly on device. And because power is such a big deal on a system like this, the thermal management is, it's still a challenge, but it's not nearly as bad as if I was to slap on some GPUs, right, that are burning 300 watts when performing inference. So as I alluded to earlier, one of the big problems with that, though, is as we push more and more intelligence on the system, current state-of-the-art technology results in a bloat of the computational hardware. And for a system like this, that's the wrong way to go. We need to be getting smaller. And so due to that challenge, our research group is looking at what can we do to make substantial contributions into bringing that intelligence to these systems at the edge without increasing the swap. Okay, so I'm not sure how to summarize this, but during our conversation here over the last 3 days, we've had a lot of really good discussion and debate. But if you kind of take a step back and listen, look at the comments that have been made, you can kind of classify them into two groups. So one thing is, if I put on my engineering hat, I'm an engineer now. I care about solving a specific problem in a specific amount of time because I need, to get to market or whatever it is, right? There's answers that are driven more by an engineering design. I'm solving a problem. If I take off that hat and I put on my science hat, there's been other comments that have been motivated because we want understanding. We don't care about solving a specific problem. We're just trying to understand, right? So those two perspectives are frequently conflicting, especially as we discuss. But that conflict is a good thing because it helps us have diversity of input as we, as a community, try to advance our effort. So why am I saying this? Our group has recognized that there is a very large community out in society who is dumping millions of dollars and millions of hours of labor into the traditional ML approach. And our neuromorphic community, as again, I'm preaching to the choir here, is a very, very small community. So we've signed up to push on applying neuromorphics even to problems that it may not make the best sense, but we have to find the boundaries of where it's going to fit. And we have to push to the point to where we either answer that question or not. Is it going to work here or not? And so that is a big reason why we're doing this research, is we're running with that. We're joining all of you and picking up that baton to try to push to find that boundary, because we have needs. We have to address this edge intelligence problem. Okay, so with that background, here's kind of a little roadmap of what our specific group has been working on. For those of you who may not be familiar with the U.S. DoD terminology regarding research, if you look above the black line, in the military we call 6.1 research. That's basic research. And as you start to become more and more applied, the number grows. So 6.2 research is still, it's close to basic, but it's like you're now applying it to a problem, but there's no mission, there's no specific problem that you have to solve, but you're just applying it. These are kind of the bottom two rungs of the research TLR ladder. And then the number goes higher and higher, right? So that RSGS program that I was talking about, it has a mission, it's got a flight date. You know, that was a little r, big D problem, whereas these are more big R, little d kind of problems, if you follow the analogy there. So for the sake of time, I'm going to introduce you to just a high-level introduction to two papers that some of us worked on. And then I'm going to talk about a few applications, one of which is a collaboration that we're doing with Ed. So, all right, so about, I don't know, 16, 18 months ago, we published a paper called spike-propamine. It was our first look into differentiable plasticity in spiking neural networks. So basically what this means is it gives us, it's a study that we looked into the ability to, during an offline gradient descent training of an agent, not only do we train the base policy to get the base weights, we're also determining the optimal parameters that govern synaptic plasticity for online learning during inference, okay? We primarily use reinforcement learning because of the robotics problems. We're not using DeepQ networks like Ed, we're primarily doing on-policy PPO based trainings, but this technique was a first way for us to use gradient descent to optimize the synaptic plasticity parameters that govern the online learning. And we found some nice results, increased robustness to noise, and we were able to solve some problems that standard SNNs weren't able to, or I should say non-plastic SNNs were not able to. And if you want to know the details, you can find that in Frontiers in Neurorobotics. We've got another paper that's about to come out in Frontiers of Neuroscience. This one is an extension to the spike-propamine effort. We call it meta-spike-propamine. But basically, this is a meta-learning paradigm based off of the spike-propamine differentiable plasticity. And I'm going to try to describe this at a high level. I'm not going to dwell on it. If I confuse you, just come talk to us afterwards. But at a high level, think of it this way. There's two networks. One network is non-plastic. Second network is plastic. There is a nested dual loop training process. The outer loop is done offline. And during that outer loop, it trains the non-plastic network to be to generate neuromodulatory signals to modulate the plastic network. At the same time, during that outer loop, we're also doing all the spike-propamine stuff that I mentioned on the plastic network. So we're getting the base policy on the plastic network, and we're optimizing the parameters for the synaptic plasticity. So what that means is during the optimization process, we're teaching the network how to learn and solve problems that it's never seen before. So such that during inference, the network and the neuromodulation is able to then solve problems that it's being exposed to for the first time. These two papers are things that we are actively working on to be able to put into our robotic hardware. And we'll talk about that next. So I'd like to talk about two main applications. One is in collaboration with Ed's group on this naval robotic maintenance. And the second one is about in-space assembly. So our division has spent, I think, the last 20, 23 years working on advancing that capability to send up the space robotic mechanic, right? And it's going to launch here in 15 months, summer of 2024. We don't do any work of the develop anything of a second kind, right? Once we solve the first of a kind, we transition it off. And we have a partner for the space mechanic. It's Northrop Grumman. They're going to be taking that, and there's an entire business market. Oh, I keep clicking. There's an entire business market that's already waiting for satellite servicing. So NRL has been asking us, well, our division's been asking ourselves, what's the next thing that we're going to work on? So we have already begun doing work to where we're going to, we are researching how we can change the paradigm of how satellites are built. So today, satellites are built on Earth. They're completely constructed. They're folded up through origami into a smallish volume. They're put on a launch vehicle and they're mass lifted off the Earth and put into orbit, and then they expand out, right? The size, the maximum size of the satellite that you can build is limited by the size of the launch vehicle that you have. You really can't get any bigger than what a launch the current state-of-the-art launch vehicle technology has. So we're investigating, well, how can we build massive structures in space that are way too big to be lifted off the Earth? What's the new way to do that? So we've been investigating how to do that robotically, to where instead we have a whole bunch of little launches with little smaller launches, and each launch has a box of Lego pieces, and we have our robot in space, and the robot pulls out the pieces out of the Lego pieces and constructs up, assembles a very massive structure. So that's an active area of research that we're doing right now. We're building a robot that has 6 limbs on it. They're all identical limbs. They're 7 degree of freedom Canova Gen 3 arms. We call 4 of them legs, and we call the other 2 arms, but they're all arms. Effectively what this is it's a robot that we call a truss walker. It's able to walk along a truss, pick up the next set of truss elements, walk out to the end of the truss where the build site is, and we can assemble the next truss there, and it just keeps doing this, and eventually you build up this massive structure. So if you take a look at this kind of notional mock-up, this is a massive structure, and right up here is our tiny little robot that has been slowly building and constructing that structure. Okay, so let's look at where we're at in terms of some of our algorithmic developments. Oh yeah, okay, before we do that, at the risk of using the wrong kind of term, or I'm very quick at drinking the Kool-Aid. So there's some new technology that's come out of NVIDIA. Some of you may, does anybody know what Omniverse is? NVIDIA's Omniverse? Those of you who are doing reinforcement learning, if you are still using Gazebo or Majoko or heaven forbid, well, some of the other ones, let me just say this. We can save you lots of time if you will come talk to us. We start using the NVIDIA Isaac Gym. To give you an example, we were using state-of-the-art Majoko for many years. And when Isaac Gym came out, we just did a little proof of concept test on it. We took one of our trainings, unoptimized, on a single GPU, we got a 20x performance improvement just by translating over to Isaac Gym. And now we've done optimization, we've bought a whole bunch of GPUs, and it screams. So whereas before, when we were doing reinforcement learning with these other simulators, you can only have one environment running at a time. On a single GPU, we could spin up 60,000 environments that are all running at the same time. So the massive amount of data that you need for reinforcement learning is really fast in Isaac Gym. So because of the Omniverse platform, where it's plugging into industry standards for making professional grade graphics. Omniverse doesn't actually create the graphics. It's a glue to where you go out to Unreal Engine or Unity or any of the 3ds Max, any of these tools that are making photorealistic graphics, and it sucks those assets into the environment. And so we can literally make digital twin environments that are extremely high fidelity. And the physics are very powerful to help us during our training. So I need to get moving. Anyway, so we're using this for our trainings. Here is a 7 degree of freedom robotic manipulator from Canova. It, on the left, is showing a traditional control theoretic controller, opening up a drawer and closing it. On the right, this is a fully spiking network running on the Intel Loihi 1 Nahuku 8 board. There's a technical problem that Tim and his team's helping us out with. We had to remove one piece of the algorithm because of a problem with just the Nahuku 8. We're getting a Nahuku 32 and it works on that, and then it'll be fully deployed at that point. But so we have a fully SNN running low-level servo controller for a robotic arm that we've proven out. Next, we have anybody familiar with the Ghost Robotics Vision 60 quadruped? So it's kind of like the Boston Dynamics quadruped, but it's different. The reason why our group went with Ghost Robotics is the Ghost Robotics, just like the Canova arm, we're able to throw away their software and go all the way down to the torque level control of the joints. And we're developing SNN controllers to control the system at the low level. We can't do that with the Boston Dynamics. They don't let you have low level access. So what my really choppy, crappy videos are showing here, no offense, Sam. On the left, we have SNN locomotion policies making the dog walk around with SNNs that were trained through reinforcement learning. On the top is the Canova Gen 3 arm, again, trained with SNN policy. In the middle, we're showing those two merged together. We're putting the arm on top of the back and walking around. On the right is what we hope to be doing soon. Look at the note. That is current. That video on the right is teleoperated. Because I can't show you anything that hasn't gone through the official release process. I couldn't show you a video that I really wanted to show you, but just as of last Wednesday, meaning 8 days ago, we have the Ghost Robotics dog now walking with an ANN policy. And we are working with Tim and the Intel team. And as soon as we get that Loihi 2 hardware, we're going to be putting our SNN on and testing that out. But the SNN walks the dog in sim, just like the ANN does. And we've proven out the ANN in hardware. So we hope to be showing shortly the arm on top of the dog, all SNN controlled on Loihi. And then we give Ed a spiking system that he can control and do his tool picking and his cabinet opening with the vision work that he's been working on.
So sorry to interrupt. If you have a final slide.
Yep,
this is it.
This is my last one. Yeah,
okay.
Sorry I went long. Okay, so I talked a little bit about NVIDIA already. I will educate you about Replicator. There's a tool in the Omniverse stack called Replicator. And much like because data sets don't exist for us, like in the supervised learning community, Omniverse Replicator allows us to do data augmentation or domain randomization within that virtual environment. So when we spin up 200,000 parallel environments, every one of them will be unique. And that's not just physics, that's including textures, lighting, materials. There's a gamut there that we can spin up all of those parallel environments that are unique. We're in the process of building a digital twin of a Navy ship. We're going to put our training process of the dog on the Navy ship and give it sea legs, put the ship in sea state. So the low level locomotion policy learns how to walk when the ship's in sea state. And because I've run long, I will stop here and answer any questions that you might have.